Hello everyone, I am Peng from Cardiff University. Today I'm going to talk about a step-by-step modeling approach for silicon carbide MOSFETs half-bridge power modules by considering the temperature characteristics. When designing power electronic converters using silicon carbide MOSFETs, the device models are usually required to simulate the performance of silicon carbide MOSFETs, such as switching losses and EMI. Although most manufacturers have provided simulation models for their discrete silicon carbide MOSFETs, there are very few commercial models for silicon carbide power modules. So the designers might need to design their own models for the power module they used in order to maximize their converter performance. However, most converter designers are not expert in semiconductors. Therefore, a modeling method based on datasheet is preferred for most designers because they don't need to buy and use any extra measurement equipment, which can save both time and money. Besides, the device models have multiple parameters to model the nonlinear behavior of silicon carbide MOSFETs, which requires a step-by-step modeling approach to help the designers to extract the model parameters. The structure of silicon carbide MOSFET discrete device or power module are shown in this slide, which includes silicon carbide MOSFET chip and the package. The internal structure of the silicon carbide MOSFET chip is shown in this slide, and the equivalent circuit of silicon carbide MOSFET can be derived from the physical structure, which includes the parasitic resistance, capacitors, and the current source to model the nonlinear behavior of the channel current, and the body diode. In the equivalent circuit, the source resistance is very small, so it can be ignored in the model. In silicon carbide power modules, silicon carbide MOSFETs are usually anti-paralleled with silicon carbide Schottky diode. Comparing to the body diode of silicon carbide MOSFETs, the silicon carbide Schottky diode has the advantage of lower voltage drop when it is forward biased and no reverse recovery current during the turn-off. The silicon carbide Schottky diode can achieve lower power losses due to these two advantages. When the silicon carbide Schottky diode is anti-paralleled with the silicon carbide MOSFET, the body diode of silicon carbide MOSFET will not turn on due to the lower voltage drop of Schottky diode, so the body diode can be ignored. Therefore, the equivalent circuit of silicon carbide MOSFETs with anti-parallel Schottky diode in the power module can be simplified as shown in the right figure. The general modeling process of silicon carbide MOSFETs is summarized in this slide. Some hardware and software are required to characterize the device under test. For example, we need the double pulse tester, the power device analyzer, the thermal plate, an impedance analyzer, or vector network analyzer, and the digital simulation tools. Firstly, the device under test is characterized to obtain the IV, CV, temperature characteristics, and also the parasitics. Secondly, mathematical equations are designed to model these characteristics. Co-fitting methods are used to tune the model to match the measured data. And thirdly, the model is verified by simulating the turn-on and turn-off switching transients using double pulse tester and compare the simulation results with the experimental results. If the simulation results disagree with the experimental results, we need to go back to step 1 and 2 to improve the model accuracy. And if the model is accurate enough, we can go to the final step to simulate the power electronic converter using the model to evaluate the power losses and EMI of the converter. The simulation results can also be compared with the experiment to further verify the model. The model we used to model the silicon carbide MOSFET half-bridge module is shown in this slide. The model contains 3 parts: the IDS model, the diode model, and capacitance model. The modeling approach of IDS is based on SPICE Level 1 model of MOSFETs. The model has 4 parameters. A step-by-step modeling approach is shown in this flowchart to extract the parameters. To further model the temperature characteristics, the model parameters are modeled as a function of temperature, and the temperature dependency of the parameters are extracted using this flowchart. The step-by-step modeling approach is also proposed for diode and capacitance models to extract the model parameters. Afterwards, the model is verified by comparing the simulation results with the datasheet and the experimental results. Firstly, the static results are compared. The IV characteristics are compared under different temperatures with the datasheet, and the temperature dependency of the parameters are shown in this slide. The diode and capacitance characteristics are also compared with datasheets respectively. It can be seen that the simulated static characteristics can match the datasheet accurately. Finally, dynamic characteristics are compared by conducting double pulse test. The double pulse tester is built in the lab, and the simulation circuit is built in PSpice. It can be seen that the simulated turn-on and turn-off waveforms can match this experimental results. In conclusion, a step-by-step modeling approach of silicon carbide half-bridge power module is proposed to extract the model parameters. The model is based on datasheet, so no actual measurement is required. This modeling approach is helpful for power electronics designers to design their own models for various silicon carbide power modules. That's all for my presentation. Thanks for listening.